Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this video is part 2 of integration by trigonometric substitution. In the previous video, we talked about some forms of integrals where you might have to use trigonometric substitution to solve. Those forms were square root of a squared minus u squared, square root of a squared plus u squared, and square root of u squared minus a squared, where a is a constant and u is a function. So if you have integrals containing those and you're unable to integrate them using the patterns and methods we've talked about previously, then you can look at trig substitution as an option. I just want to point out, though, that just because you have something in one of these forms doesn't mean you're going to use trig substitution. This is an example of a general power formula. I could express this as 1 plus x squared to the negative 1/2 x dx, and my pattern is u to the n, and this is going to be part of the du factor. So I already have a technique. I wouldn't use trig substitution when one of my other patterns works. Similarly, this integral fits our inverse sine pattern, so I wouldn't use trig substitution on this either. So it's in the cases where you have integrals having functions of that form, but that you're not able to integrate with previous patterns. In the last video, we did an example that's of this form. In this video, we're going to do an example of this form and this form. Let's start with this one. We have the integral of dx over x squared plus 25 to the 3/2. So that 2 in the denominator means square root. And we have u squared plus a squared. It doesn't matter the order when you're adding. So this is the form that we're going to use. And when you're working with an integral in this form and you can't integrate it by other techniques, then the substitution you're going to use is u equals a times tangent theta. So a squared will equal 25. Therefore, a is 5. U squared is x squared. U will be equal to x. Remember, a is always the constant, u is the function. So u, which is x, will be equal to a, which is 5 times tan of theta. So we're going to place our x's with 5 tan theta. We're changing to a different variable, so we have to work with d theta, not dx. So let's find dx in terms of d theta. We differentiate 5 times secant squared theta d theta. Do our substitution, and we'll have 5 times secant squared theta d theta, replace dx. In the denominator, we will have x squared, which is 5 tan theta squared plus 25. Let's pull the 5 out. Five times tangent theta squared will give me 25 tangent squared theta. Let's factor 25 out of each term. Now let's distribute that power to 25 as well as to this. So we're going to get 25 to the power of 3/2 and tangent squared theta plus 1 to the 3/2. Square root of 25 is 5. Cubed is 125. We're going to move that out in front of the integral sign, and it's in the denominator. So it'll be 5 over 125. We have a Pythagorean identity that tells us that tangent squared theta plus 1 is equal to secant squared theta. So I'm going to replace this with secant squared theta. 5 over 125 will be 1 over 25. When I have secant squared theta to the power of 3/2, I multiply my exponents, and that will give me secant cubed theta. And I can cancel a secant squared theta out of numerator and denominator. And I can express 1 over secant theta as cosine theta. This is a function I can integrate. The integral of cos theta d theta is simply sine theta. I'm not going to put the constant of integration in yet because I'm not done. I want to write my answer in terms of x, not theta, so I need my right triangle. Going back to my substitution, I have x is equal to 5 times tan theta. Therefore, tan theta will equal x over 5. We know that tangent is equal to the ratio of opposite over adjacent. So opposite would be x, adjacent would be 5. And then to find the hypotenuse, we can use our right triangle theorem. So the right triangle theorem says that x squared plus 5 squared will equal hypotenuse squared. So our hypotenuse will equal the square root of x squared plus 25. Now that we've defined the 3 sides of our right triangle in terms of x, let's go back to our answer. Sine theta we can express as the ratio of opposite side to hypotenuse. So the side opposite is x. The hypotenuse is square root of x squared plus 25. And now I can add my constant of integration. So there are a lot of steps when you're working with integration by trig substitution. However, using this method allowed us to find the integral of something that we couldn't integrate before. Let's take a look at the last form for doing integration by trigonometric substitution. So our next example would fit this form, square root of u squared minus a squared. We've got integral of dx over square root of x squared minus 9. We can't use our general power formula on that. We can't use our inverse trig forms on that. So we're going to use trig substitution. But when you have your integral containing this, the substitution you're going to use is u equals a times secant theta. So in our example, a squared is equal to 9. So a is equal to 3. U squared is equal to x squared. So u is equal to x. Therefore, I'm going to let u, which is x, equal a, which is 3 times secant theta. I'm going to differentiate that to find dx. So it will be 3 times the derivative of secant theta will be secant theta tan theta d theta. So I'm going to plug those in for x and dx to get that. I'm going to pull the 3 out front of my integral sign. I'm going to square this, it will be 9 secant squared theta minus 9. My next step is to factor out a 9 in this expression. Then I'm going to break up the square root of 9 and the square root of this expression. So square root of 9 and then square root of secant squared theta minus 1. Again, we're going to use a Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. Therefore, tangent squared theta is equal to secant squared theta minus 1. We're going to replace secant squared theta minus 1 with tangent squared theta. I'm going to take the square root of 9, which is 3, and pull it out in front of the integral sign, so I'll have 3 over 3. The square root of tangent squared theta is just tangent theta, which I can cancel that factor. So now I'm just finding the integral of secant theta d theta. We can integrate this. We already have a pattern for this in our basic trig patterns. The integral of secant theta d theta is the natural log of the absolute value of secant theta plus tan theta. And I'll worry about the constant integration when I'm done. I have my integral in terms of theta. I need it in terms of x. So let's set up our right triangle. Here's theta. We know that x, it will equal 3 times secant theta. So x over 3 will equal secant theta, which also means that 3 over x is equal to cosine theta. So you can think of it either way. In either case, if we look at it as cosine, cosine is defined as the ratio of adjacent to hypotenuse. So the numerator would be the adjacent, the hypotenuse would be the x, and now we want to find this side. So we use our right triangle theorem. 3 squared plus that unknown side squared will equal x squared. That unknown side squared will equal x squared minus 9. So the opposite side will be square root of x squared minus 9. Now that I know all 3 sides, now I can go back and replace these trig functions and write in terms of x. So this will be the natural log of secant of theta. Well, we already know secant of theta is x over 3 plus tan of theta. Tan of theta will be opposite over adjacent. And now we'll write our plus c. We can combine these fractions, so it'll be x plus square root of x squared minus 9 over 3. And you would be correct if you left it like this, but if you looked up the answer, the author might go a little bit further with this, and I just want to show you what could be done and what you could see. According to the properties of logarithms, we can split this up into the natural log of the numerator minus the natural log of the denominator, and it's positive so I don't need my absolute value signs. Natural log of 3 is a constant. We can punch it into our calculator and get a number. So if we were to absorb that with this constant, we could write this as the natural log of this plus some other constant, where that constant represents these two constant combines. And you might see it with just a regular c, but I want you to understand that when you combine an arbitrary constant with a specific constant, you still get a constant. So you might see it written in this form instead of this form. So practice finding these integrals using trig substitution. Once you've done a few, it becomes easier. I know it's a lot of steps, but just remember what trig substitution to use for the particular form you're dealing with. Then express x and dx in terms of theta, simplify it, and hopefully you end up with something you can integrate, and then go back to x using your right triangle. Integration involves a lot of different patterns and approaches. We've talked about a number of those patterns, and we've talked about integration by parts. This is just one more technique that you can add to your tool belt. Take care.